Please start with this file titled H atom. H atom.
Yes, sir. She will do that in a second. Let her
Ha.
just start
The,
the recording process, and after that, she will do exactly as you instruct her.
Yes, ma'am. Now recording has started and we are live now. And
So,
I'm sharing the
yeah,
introduction
yeah,
slide.
yeah. Please share his introduction slide first.
Ma'am, just a minute. Ma'am, is my screen visible?
Yeah, it is visible.
Ma'am, slide is visible? Yeah.
Yeah, here it is.
Yes, ma'am.
Yes, yes, yes. Now it is visible. Absolutely. Okay. Participants, we once again have the pleasure of having Dr. Partha Goswami amongst us once again. He has contributed immensely to this program and for your benefit. So thank you, sir, and I welcome you once again. Poonam, that is lost. What has happened? Yeah. It is my pleasure to introduce Dr. Partha Goswami to the participants once again. Dr. Partha Goswami is MSc, MPhil, and PhD from University of Delhi, and he's currently an associate professor of physics in Deshbandhu College, University of Delhi. He has done his graduation with first class first position from St. Xavier's College, Ranchi. He has been teaching mathematical physics to BSc Physics honor students for the past 30 years. His area of specialization is condensed matter physics theory. He has had 2 research papers to his credit, mostly under sole authorship, published in prestigious journals of physics. Dr. Goswami, welcome you, sir. And
thank you. Thank you.
yeah, and I invite you to start your lecture. Poonam, please start sharing his PPT.
Yeah. Thank you, ma'am.
Most welcome, sir. She will just share your slides in a second.
Hello.
Yeah, yeah. She is just sharing, sir. You'll be able to
Yes,
see
sir.
now.
Is it
Yeah,
visible now?
Yeah, visible. Visible.
please,
Visible.
please make it full screen, Poonam.
Yes, ma'am. It is going, ma'am.
Yeah.
Yeah. Okay. So can I make a start now?
Yes, sir. Please tell
Oh,
us.
okay.
Tell us.
Okay. Yeah. The our goal, if I'm given a few lessons starting from today, our goal would be to solve time-independent Schrodinger equation for a variety of one-dimensional potential functions. That is, we want to find the energy levels and the corresponding energy eigenfunctions for quantum particle subjected to a variety of types of forces. Some of these examples will have important real world applications. For example, to molecular vibration or to electrons in semiconductors. uh, Dr. Jogesh has already given you a great exposition uh, to the solutions of infinite square well and related problems. So a logical next step would be to pick a slightly more complicated potential. Well, one should have taken up a square well with finite depth, or a smooth potential of a simple harmonic oscillator, as all such things. But uh, I, for some reason, which I'm explaining shortly, I chose Coulomb potential. Reason being, this is in the syllabus of uh, our Delhi University, and the entire theory, at least the radial part of the solution, has to be worked out analytically, and angular part, well, uh, uh, in theory, of course, one has to, but in experiment with MATLAB or Scilab, one need not worry about the angular part. So I thought it better to make a jump and go directly over to the Coulomb's potential. And thereafter, we can discuss screened Coulomb potential, harmonic oscillator potential well, or anharmonic oscillator potential well. All such potentials are in the syllabus of Delhi University theory, quantum mechanics theory, as well as experiment. Experiment is the user the package that is used for such exercise in experiment is Scilab generally, or it could be even MATLAB. There is no hard and fast restriction. Now, there are a few things which, of course, one needs to know, and that is the solutions to time-independent Schrodinger equation have several interesting properties. What are these properties? The solution psi x will represent some state of the particle that say that would give me the expectation value, and that expectation value will never change with time. I think our students are already familiar with expectation value. It is a slightly complicated, though mathematically simple, but theoretically slightly complicated idea. But anyway, if they are familiar, I don't want to discuss this. I straight away say that the solution must represent states of the particle that will give me expectation value that do not change with time. Wave function may change with time, but expectation values will remain constant. And second uh, feature, second property is that the solution psi x would represent some state of the particle that will have definite total energy. The statement 1 and 2 are actually somewhat similar. They may appear, but there is a great difference. The difference is that suppose I am given a Hamiltonian with a certain potential, and TISC, time independent Schrodinger equation, tells me that the Hamiltonian operator acting on psi will give me energy times psi. And expectation value of Hamiltonian operator will be, as I'm sure students are familiar with this, integral of psi star x, Hamiltonian operator acting on psi x, and integrated over all space. And Hamiltonian operator acting over psi will give me energy times psi. So we shall have energy being a scale number. It will come outside the integral. So we have in energy integral psi star psi, which is just the energy as we expect. Now suppose I take expectation value of square of the Hamiltonian, I would get E square. So when I look at the variance, what is variance? Variance is expectation value of square of the Hamiltonian minus square of the expectation value of the Hamiltonian, and that would become 0. So what does this mean? Variance being 0, every measurement of the energy must be the same, and namely E, the energy. And general solution for a particular potential will be a linear combination of stationary state solutions. I'm sure people have already understood what stationary state solutions are. So a time independent Schrodinger equation has in general an infinite number of stationary state solutions, psi 1, psi 2, psi 3, each having different uh, energy, E. So a solution to one of the solutions to TISC is of the form, say, psi 1x into exponential minus I E1t upon h cross, if it has to be a stationary state solution. And general solution will be linear combination of all these solutions, that is Cn, Psi-n. Cn is, of course, the multiplier to achieve the linear combination. Sum of Cn, Psi-n, exponential I, E, and t upon h cross, where sum is over all n from 1 to infinity. And regarding the properties of psi, I'm just, in a way, I'm recapitulating if students have in the process forgotten. Psi must be finite. Uh, this is derived from the normalizability of the wave function and from the requirement that dynamic quantities that we extract from psi also must be finite. And psi must be single valued. Uh, if psi is not single valued, then expectation value one derives from it are undetermined, which of course is an absurd situation. Psi must be continuous. If psi is not continuous, then d psi dx will not be finite. And as we all know, d psi dx into h cross I corresponds to momentum operator. So momentum operator in that case will go to infinity, unphysical situation. So psi must be continuous. D psi dx also must be finite because momentum would be finite. So d psi dx must also be single valued. So these are the requirements that we impose on psi. So with this background, now I go to the first slide of mine, and since we are considering Coulomb's potential, and in effect it is a single electron system that we are considering, that is H atom, not even uh, H hydrogen like atom, because uh, helium plus, beryllium plus plus, sodium 10 plus, they are all going to be hydrogen like atom, single electron system, but they have uh, uh, actually uh, not a single proton. They have, for example, in sodium, we shall have 11 protons. So we are considering the problem of H atom only, and it is a single electron system. Problem has spherical symmetry. So most desirable, therefore, it is desirable for us to use r theta phi spherical polar coordinates. and in three dimensions. In three dimension, of course, it is a three-dimensional problem. Unlike which Dr. Jogesh had been discussing, mostly he's been discussing a one-dimensional problem. So this is a three-dimensional problem. But we are not using, I say emphatically, Cartesian coordinates. We are using spherical polar coordinates. So our Hamiltonian operator would be in no matter whatever be the coordinate. For a single particle, h cross minus h cross square upon 2m del square is going to be our Hamiltonian operator. So I have written that down at the top in the slide. One can see that minus h cross square upon 2m, and within parenthesis I have the expression for del square in spherical polar coordinate, that is in terms of r theta phi. And this del square minus h square upon 2m del square is acting on psi, plus I have the potential term, which is going to be the Coulomb's potential minus E square upon R, because I am considering hydrogen atom, single electron system, and there is one proton in the nucleus. So minus E square upon R psi or VR psi equal E psi. This is our TIAC in spherical polar coordinate for hydrogen atom. Now, given this equation, the TIAC, time independent Schrodinger equation, psi, of course, will be a function of r theta phi, and this is a differential equation. So, as we all know, in a differential equation, we do the technique to solve the differential equation is to have separation of variable. So psi r theta phi I would write as radial part capital R, which is function of small r, the coordinate, and angular part y, which is function of a polar angle and azimuthal angle, theta and phi. So I have written down psi as in separation of variable technique, psi equal capital R into y. Capital R is the radial part, y is the angular part. Angular part y is called they are called spherical harmonics, and I shall, if time is given to me, time permits, we shall show that capital R is expressed in terms of associated Lagrange functions. I'm sure all of us have, our students have studied differential equation, second order differential equation of first degree with non-constant coefficients. And I'm sure they have solved those equations by series solution method or extended power series solution method. So there are a variety of equations which is taught in Delhi University. For example, we have Legendre equation, we have associated Legendre, we have the Hermite equation, we have also Lagrange and associated Lagrange differential equations, we have Bessel differential equation, and so on. So these are typically in the syllabus of Delhi University. So Lagrange differential equation will have solution, of course, in terms of a polynomial, which is called Lagrange function. So we shall later on show that radial part, in fact, transforms into associated Laguerre function, not precisely Laguerre, associated Laguerre. Associated Laguerre is in fact derivative of Laguerre. So that is the first slide. Please go to the second slide. Please go to the second slide. Second. Yeah. Okay. Second, yeah. This is it. Okay, so everyone can see at the top, I had written down del square in terms of r theta phi. The term in the within the parenthesis actually is square of the angular momentum operator upon h cross square. So, assuming spherical symmetry, which is there in the problem, the Laplacian could be written down as d2 dr square plus 2r del r minus square of the angular momentum operator divided by r square h square. So our Schrodinger equation for hydrogen atom becomes h psi equal minus h square upon 2m, the Laplacian operator del square plus VR potential whole multiplied by psi equal E psi. The hydrogen atom, in case of hydrogen atom, the complete set of commuting variables is H, L square and Lz. Why? It could be easily shown that commutator of our Hamiltonian and L square is equal 0. Similarly, commutator of Hamiltonian operator and Lz, the zth component of the angular momentum, is 0. So complete set of commuting observables for our hydrogen atom problem will be Hamiltonian itself and square of the angular momentum operator and the zth component of the angular momentum operator. Now I go to the next slide, wherein please go to the wherein with detailed algebra I evaluate the commutator of Hamiltonian, hydrogen atom Hamiltonian and L square and show that it is equal 0. I'm sure everybody here is familiar with commutator. The basic idea, one of the basic ideas of quantum mechanics is that observables are no more numbers. They are represented by operators. Operators could be in your Schrodinger formalism, differential operator, in Pauli and Hassenberg formalism, matrix formalism, they could be square matrices. It is very easy to see, at least for matrices, that commutation relation is not by A into B, product A into B is not necessarily equal B into A. So operators in quantum mechanics need not necessarily commute. And in that case, it is legitimate to calculate the commutator of say operator A and B. Commutator is defined as, it is written as square bracket A comma B, square bracket closed, and it is equal operator A B followed by B minus operator B followed by operator A. If the operators happen to commute, then this AB into BA minus BA would be 0. If they don't happen to commute, then AB minus BA will be non-zero. The most fundamental commutator that I'm sure you have come across already is your X commutator of position and momentum operator is equal IH cross. Hello, have you seen this? Have the students seen this fundamental commutator?
Students, please respond in the chat box so that I can revert to sir. Yes, sir.
Okay, very good, very
One
good.
of, yeah.
What does physically commuting mean? If the two operators commute, what does it mean physically? If the two operators do not commute, what does it mean physically? Do the students have this idea? Hello, students, do you have this idea? Physically, because
Students, please respond.
we are not doing mathematics. This is not a mathematics course. At the end of the day, it is physics course. And you need to understand physically what does this mean. Hello?
No, sir, I don't think so. Ki students are having this idea. One of the student is
Ah,
writing if they
ah,
commute, they can be measured simultaneously.
very good, Akshita Goel. You have understood that the commuting operators are compatible, and since they are compatible, simultaneous measurement of both the operators or operator actually correspond to some quantity. So simultaneous measurement of the two corresponding quantities is possible to an arbitrary degree of precision, meaning thereby that suppose A and B correspond to two quantities, and the operators are corresponding operators are denoted by A hat and B hat, and suppose A hat and B hat commute, it means the operator B, A and operator B together can be measured to any degree of accuracy, right? Whereas if the operators do not, so Akshita was absolutely right. So, whereas when operators do not commute, what does that mean? It simply now means that they cannot be a simultaneous measurement of such operators is not possible to any degree of accuracy. That term has to be added to an arbitrary degree of accuracy. For example, position and momentum, they do not commute. Their commutator is IH cross. So I have the uncertainty principle with involving these two quantities, the uncertainty in position, uncertainty in momentum product is greater than equal h cross by 2. H cross is reduced Planck's constant, which means what? Which means simply that if you determine position to a very to a highest degree of precision that you have access to, then momentum of course will go haywire, accuracy will go haywire, and vice versa. So this is what commuting and non-commuting mean. So Hamiltonian here, hydrogen atom Hamiltonian in spherical polar coordinate, and expression for L square, which is also given here in this slide, square of the angular momentum, Not spin angular momentum, mind you. This is orbital angular momentum I am talking about. With electron, you have orbital as well as spin. The spin magnetic moments or corresponding mechanical quantity angular momentum. So we are talking about orbital angular momentum. So square of the angular orbital angular momentum and Hamiltonian, they commute. That means for hydrogen atom, simultaneous eigenstates for the two quantities are possible, or both could be measured together to to an arbitrary degree of accuracy. Please go to the next slide. Yeah, in the next slide, similarly, I have shown that in the next slide, similarly, I have shown in detail because uh, uh, at least once one should go through, that's what I feel, one should go through whole calculation to get the heck of everything. So, therefore, I have tried to give as much calculation as possible. Commutator of H and LZ also is zero. I have shown it in detail. With all this, I did not discuss it actually. If students go through these two slides carefully, I'm sure they would understand. No big deal. I'll go to the next slide, which is separation of variable. Next slide, please. Next one. Yeah, separation of variable. I did it hurriedly, so I had no time. I had to write and then put it in the slides. Uh, so, as I said, to have solution of this problem, hydrogen atom problem, we do the separation of variable. We have written psi as radial part r and angular part y, and we have put this in our time TISC, and then I had divided this equation by r and y, and also I have multiplying by r square and rearranging the terms, which I'm sure everybody can do. I get the equation which is written at the end of this slide. No big deal. It is only mathematics. There is no physics involved. We have done some slight manipulations, and these manipulations, what I have done is I have clearly jotted it down. So if a student tries to follow this, I'm sure a student will not have any difficulty. So we go to the next slide then. Uh, uh, well, we have to remember that in our previous slide, we had curly braces, terms within curly braces, and terms within square braces. So the two terms in the curly braces depend on R on, and two terms in the square brackets depend only on angles theta and phi. So only way the sum of the groups can be zero, which is zero anyway, is if each group is equal same constant. So we make the choice of the constant as L into L plus 1, where L is the angular momentum quantum number. Why I am making this peculiar choice? The student might ask, why L? Why not C? Why not K? Well, there is a reason for it, which could be explained later. Right now, I say that you need to have two groups equal some constant. So let this constant be L into L plus 1, where L is angular momentum quantum number. So we have the radial part equal L into L plus 1, which is our radial equation, and we have the angular part equal minus L into L plus 1, which is our angular equation, and their sum is equal 0, which is what is your Schrodinger equation is. So therefore, we have been in a very cozy manner, with not much of difficulty, we have been able to separate the equation into radial part and the angular part. Now we shall focus presently on the radial part. That, of course, is more important because we go by our what is required in the syllabus. Therefore, now just to complete the formality in the, please go to the next slide. Please go to the next slide. Yeah, just to complete the formality, I deal with slightly deal with the angular part, write the angular part y theta phi as some function of theta f theta and some function of phi g phi, and I write down equation in terms of, similarly after a little manipulation, in terms of f theta and g phi. Again, same, first two terms will depend on theta and the last term will depend on phi. So non-trivial solution such that the sum is 0 is possible if the group of terms, each dependent on single variable, is equal to same constant. So we pick the constant m square as the separation. Later on we shall identify m as the our yet another quantum number. So separation of variable story over, we go to the next slide, and which is our rewriting the angular part as f theta. First equation, equation 1 is involving the function f theta, equation 2 is involving the function g phi, and we are getting, and we have introduced m square, the constant, and magnetic, this is our magnetic quantum number. In fact, this is how magnetic quantum number is introduced. Equation 2 has very trivial solution. It is harmonic oscillator type equation. So solution is gm phi equal exponential im phi. And in equation 1, we change the variable from theta to x, theta to x, and we get the equation 3. This is our associated Legendre equation, right? And it reduces to Legendre equation only when m is 0. So solution to this equation, equation 3, which is for f, will be associated Legendre polynomials, which I have written down in terms of Roderick's formula. I'm sure people are familiar with these terms. PLM, because now two quantum numbers specify the solution, L and M. So PLMX equal minus 1 to the power m and square root of 1 minus x square whole to the power m, and m is the derivative of a Legendre polynomial. So bottom line is one has to be uh, totally, absolutely familiar with the these functions, Legendre, Bessel, Lagrange, Hermite, and so on. Then and only then understanding what I am saying would be possible. And things which I am writing will appear too simple to whoever had understood and had mastery over these polynomials, standard polynomials. So up to this, we had touched upon the angular part and had not touched so far the radial part. Now we can go to radial part. I have another set of slides. Dr. Poonam, I have another set of slides by the title Hydrogen
Yes, sir.
Atom. So can
Yes,
you
sir.
project those slides where I would
Yes,
discuss
sir. Yes, sir.
radial part in detail?
Yes, sir. Just give me a minute.
Okay.
Yes, sir. Is it fine?
Yeah, hydrogen atom. Please focus on the next slide. Share the next slide. Next one. Yeah, yeah, yeah.
Yes, sir. I am on the next one.
Okay, okay. So we have the radial part here. This is what is more important for us, at least from exam point of view and other stuff. So this is the radial equation, the one at the top, which I already have derived in the previous set of slides. And I have found out the derivative of r square ddr and r multiplied first by r on both sides, and radial part capital R is to be solved for. Derivative evaluated in the third step, and Coulomb's potential written down. uh, I have deliberately put Z. Actually hydrogen atom hai, so Z should be 1. Therefore, no need to get panicky seeing Z here. Z is simply the atomic number, and for hydrogen atom, it is 1. And K, of course, one knows 1 upon 4 pi epsilon naught, which is 9 into 10 to the power 9 Newton meter square per Coulomb square. And because we are uh, Bohr had assumed, and everybody had assumed, that in fact one knows that the separation between the nucleus and an electron, say in hydrogen atom, is too vast, too vast. Nucleus has dimension of order 1 Fermi, and uh, electron orbit, say first Bohr's orbit is 0.54 angstrom. So, which means roughly 1 angstrom, 10 to the power minus 10. So, nucleus occupies a very small fraction of the total volume of the atom. So what is there in between, in the intervening space? Well, people have assumed it is free space. No one knows, no one has gone inside the atom. Uh, but if you assume free space, then in SI system, you need to put K, which you all know. K is 1 upon 4 pi epsilon naught. So that is the story in short. So we have R, writing R is somewhat misleading. So in the fourth step, I have switched to psi R. Here psi R means that same capital R as a function of small r. So I would get the d2 psi dr square. Psi is capital R. 2 by r d psi dr and this potential and energy term, and L plus 1 psi r, which had been adjusted and written down in terms of an effective potential finally minus half d2 psi r dr square minus 1 by r d psi dr effective potential, which is function of R and L both, and effective energy, which is 2m by h cross square E. So this is how the radial equation looks like at the end of the day. Now, I have no problem, but uh, even my students don't like this d psi dr term. They always, with Schrodinger equation, they are tuned to the fact that there should be second derivative of second spatial derivative of psi. So, and first derivative they are not somehow, I don't know why, although there is no reason, they are not compatible with. So anyway, then psi needs to be removed. Yeah, sorry, first derivative of psi needs to be removed by making some substitution for psi, and which is what we do in the next slide. In fact, I have in the next slide uh, at the bottom, equation 10.9, I have made a substitution. Say y is the variable which I have defined as r in the small r into capital R. So capital R or psi becomes y divided by r. This is the substitution we make, and we expect that with this substitution, first derivative will go away. How? Let us see in the next slide. In the next slide, sorry, go to the next slide, please. Yeah. We make this substitution, evaluate the derivative. It is all evaluation of the derivative. And as you can see, at the end, you are left with r d2y dr square, and this substitution serves us to eliminate the first derivative of psi or capital R. So bottom line is we shall have both first and second derivative if I want to retain the term capital R or psi, but if I go over to a new variable y, which is defined as small r into capital R, then we shall be left with only second derivative, and that is, as I said, a compatible situation for our student. So how compatible? Let us see in the next slide. You can see in the next slide with this substitution, ultimately, uh, and you make another substitution as well. Epsilon by 2 square equal to mu or m, mass, E upon h cross square. And ultimately with this substitution, equation reduces to, in the last line one can see, d2y dr square 2 mu e square r h cross square epsilon square by 4 minus ll plus 1 r square into y is equal 0. So which is something very comfortable, because ये जो स्क्वायर ब्रैकेट के अंदर टर्म है, which could be again interpreted as some kind of, if actually it will not be potential, the term 2 mu e square upon rh square minus ll plus 1 upon r square will be potential, and e square by 4 yr has to go to the right hand side. So anyway, the form of the radial equation now is a very comfortable form, and one can then uh, but notice please that your energy has changed through equation 10.20, right? So ultimately you are interested in energy eigenvalues, capital E, not epsilon. Please know that. And so is, you are not interested ultimately, you will be getting Y, but ultimately you are interested in calculating capital R. So please do not lose sight of these two facts, that okay, you have had a comfortable equation, but this situation doesn't mean that you solve for epsilon as energy eigenvalue and energy eigenvector yr, and that's the end of it. You will, of course, you will solve for these, and then you will go back and get the energy capital E, energy eigenvalues, and corresponding eigenvectors capital R. Please make this somewhere, put somewhere at the back of your mind. With this, we go to the next slide. Well, the exercise continues. In fact, I have made another change of variable for our convenience. I have gone from R to, this is dependent. So far we were changing dependent variable. Now I have changed my independent variable as well, X, that is. Sorry. Our R. Small r was the radial distance, which is our independent variable. We are now defining a new variable in place of small r by the definition x equal r epsilon, or r will be then x upon epsilon. Now please make a note, because this is somewhat confusing, and I have found, to my dismay, that even the experienced people get confused. Once you put x, you think that you have gone to Cartesian coordinate, or you treat, alternatively, you treat hydrogen atom problem in Cartesian coordinate. This is, although you can do, there is nothing like that you cannot solve in, because it would become complicated. hydrogen atom has spherical symmetry, so it has to be treated in spherical polar coordinates. And besides the x that I have introduced here, independent variable is by no means a Cartesian x. It is just a variable. So with that x, I have, why am I cautioning this? Because in the net, I have found, to my dismay, some garbage floating around. They have solved hydrogen atom problem by in one dimension, and that too Cartesian one, which of course doesn't make sense at all. So please be aware of such uh, fake ideas or unphysical ideas. So with the introduction of new independent variable, I am getting my radial equation in the form 10.22. And in fact, 10.22 is our previous equation, where L into L plus 1 was k square minus 1 into 4. So please go to the next slide. And in the next slide, seventh, that is, 2 mu E square upon H cross square epsilon becomes 2j k plus 1 upon 2. So in terms of the quantum numbers j and k, we find the solution to be as written in the equation 10 below equation 10.24. We find that we have an exponential term, some power of x, k plus 1 by 2, and associated Laguerre polynomial. How we have got it? Well, as I said, this equation, which one? Please go to 10.22, that is previous slide. 10.22 and 10.23 together resemble what is known as associated Laguerre equation. So it is not surprising at all that the solution at the end of the day is our associated Laguerre function. So as I said, familiarity with these polynomials, various standard polynomials, is very much necessary. And to calculate the energy eigenvalue, we have found we had in equation 10.23 k square minus 4 as LL plus 1. So k square becomes 2L plus 1, or k is 2L plus 1. Therefore, since k is 2L plus 1, 2j plus k plus 1 whole divided by 2 will be j plus L plus 1. So from the discussion on the associated, we go to the, please go to the next slide, 8th slide, that is, 8th slide, 8th, yeah. Since k is 2L plus 1, 2j plus k plus 1 by 2 will be j plus L plus 1. And from discussion on Laguerre polynomials, indices j and k are non-negative. And the sum j plus L plus 1 can therefore assume any integer value, uh, say of value of f of 1 or greater. We are going to rename it as n. So n is j plus l plus 1, and this new integer index n is called principal quantum number. And we now go to the next slide. So our from equation 10.24, we find 2 mu e square epsilon h cross square is equal to j plus k plus 1 by 2, j plus l plus 1 equal n, or epsilon is equal to mu e square nh square, or epsilon square will be 2 mu e square nh square whole square. And upon substituting this into 10.20, your 10.20 was earlier in the slide, I think it was sixth slide, is where you had 10.20. So upon substituting this in 10.20, e by 2 whole square, which is e by 2 whole square equal to minus 2 mu capital E h square, I finally obtain E energy as minus h square upon 2 mu a naught square n square, where a naught is our Bohr radius, first Bohr radius, which is h cross k, h cross square. K, of course, is missing out here, I'm sorry. K h cross square mu e square, and it would be 0.5286 angstrom. So this is the energy eigenvalue, and I'm sure the students have seen this at their +2 level in Bohr's theory. So we are getting the same result for radial part at least, what Bohr had obtained in his primitive quantum theory. So, well, same result for energy eigenvalue. Now, how to express the energy eigenvector? I have, go to the next slide, please. 11th slide. 11th slide. Yeah. So energy eigenvector YNLR will be exponential R upon NA0, written out in Bohr's first Bohr radius terms, 2R NA0 L to the power L plus 1 and Laguerre polynomial, associated Laguerre polynomial. And as I said, ultimately I have to go back to capital R. So I have gone back to capital R and found this to be the solution. So our eigenfunction depends on N and L. N and L, as we can see. Using the orthogonality relation, etc., of associated Laguerre polynomial, constant A could be evaluated using orthonormality relation, and after evaluation you get this kind of formidable expression which I have written down. So RNL therefore is your in 10.28 is this kind of formidable relation. Now appearance is formidable though, but if you have studied associated Laguerre, that wouldn't be difficult to calculate. And as I have done it in the 13th slide, please go to the last slide, 13th slide, 13th straight away, 13th, last one. Yeah, I had calculated few orbitals, R10, which comes out to be 2A0. A0 is Bohr radius, minus 3 by 2 exponential R minus R upon A0. Then R10 is what? This is first orbit and subshell is L equal what? 0. That means Sth subshell. So first orbit contains only Sth subshell, as we all know, which can accommodate 2 electrons. Similarly, I have R20. This is second orbit, Sth subshell. This can also accommodate 2 electrons. We have R21, second orbit, Bohr's orbit, and pth subshell, for which L is 1. So we have the radial part given in this manner. Then third orbit, Sth, pth, and dth subshell. So reading this out, once you know the expression for Lagrange polynomial, writing these formulas out is too simple. No rocket science, please. Don't get scared that this is too much of mathematics. So I believe I have taken a very long time. Isn't that so? Hello?
Yes,
Hello?
sir. Yes, sir.
I have taken, I think, very long time. Are students still there or they have gone?
Yes, sir. 70 plus students are here. Uh,
Okay, very good. Do they have any query to make?
no, sir. Till now, there is no question in the Zoom and on the YouTube.
Supriya Gupta says to everyone, yes, sir. Means they have query or
No,
don't
no,
have query.
sir. They are answering when you were asking if students are here or not. So she is saying,
Okay,
yes, sir, we are here.
okay, they are here. And they have no query.
No, sir, not yet.
That is a little bad.
No, sir, they are.
From
You are
from my
explaining
perspective,
so well.
no, I don't think so. From my perspective, it means students are not interested, so they have not they just let it go. So they don't
Sir,
have any question.
these
Anyway,
are the students. Sir, these are the students who have attended your quantum mechanics class. These are also the students who attended your EMT class. They're also the students who attended your classical dynamics class. 60 of
acha, same student,
they're
same.
the same
Okay,
students who are
okay,
going on listening to you from 27th of July. So, and I know
okay, okay.
honestly,
Uh, uh,
sincerely, there are new 30 ones, but there are almost 50 students are the ones which have been going on listening to you since first day. So don't doubt their listening or intention at all.
No,
It
no,
was
intention I'm not doubting. Maybe my presentation is too boring. So, well, your students are
no sir,
always
no sir.
right.
This takes
Uh,
time. Hydrogen atom takes time to listen to, re-listen and redo. Only then only it seeps into the head. They've heard of you in
exactly.
quantum
So,
mechanics.
you
They,
are going to put it anyway in YouTube, so they would do that.
plus, you are live on YouTube and it will be there forever. They will refer it
Ah,
many times.
yeah. I'm sure. So,
Hydrogen atom takes a long time to get embedded into the brain. So therefore, one cannot have immediate questions. I mean, I don't remember. I also had immediate questions. I had to take some time to get it into my head as a student. So I think the teaching
so
style.
Abhiram Singh says we are for quality and not quantity. What does that mean,
It
Abhiram
means
Singh?
it means, sir, Abhiram wants to say he gives very good feedback very quickly. So that he is the first one to that is my reply. What he means to say is that you are covering the syllabus slowly and nicely, and that's the quality work because of which they're sitting since 3.5 hours. It's already 3.5 hours they've been sitting. So I think that's applaudable.
Okay, whatever.
Substantial. You're
Actually,
teaching very nicely. Please
as
continue.
a teacher, you get the reward only when the students are appreciating. If they are not appreciating, what are we for?
Yes,
So that is why
very true, sir.
I
Very
was.
true. Very true. But sir, you were teaching fine. Please continue and finish your slides because after all, 3.5 hours they've been sitting. So
No,
kindly continue.
today I think this is good enough. I would like to, if at all Dr. Punita gives me time, I would like to discuss, as I told her, even numerical solution, because that
Okay,
part
sir.
is
So, okay, sir,
that.
we will schedule we will schedule 1 hour for you. So you that's not a problem, sir. We will schedule 1 hour for you in the coming 2 3 days itself.
Yeah.
We will do
Okay.
that if the students are interested in understanding this properly. Then no, it's no problem, sir. We will schedule.
Yeah, because I found that my students had taken very long time, repeated 4 5 times explanation to digest the numerical solution part.
Yes, sir.
So,
It is like that, sir. It is like that.
uh,
Sir, I'm scheduling another hour
so
for you in the coming 3 days. I will speak to
right,
you myself. Yes, sir.
uh,
Please finish this
right.
particular slide and then we will wind up for today.
This is
And
over.
we
Uh,
can continue another day. No problem, sir.
right. This is over, and I'm very thankful to all of you. And our students also who have been very patiently listening to me.
Sir,
So can
there.
I
Okay.
leave? Can I leave
Excuse me,
now? Uh-huh.
sir. Excuse me. There is a question from Anudeep.
Mhm.
Are these exact solution possible for helium-like atom also?
Helium plus, of course, matlab singly ionized, because that is one electron system. But helium per se, which is two electron system, no exact solution possible. And one then goes to variational method and all kinds of other methods, right?
Okay, sir.
Because till
Very true, sir.
date,
Very true. Sir, very true.
till
Only helium plus ion can is exactly solvable because it
yeah,
becomes like hydrogen. But
yeah,
for two
till date,
electron atom like helium, perfect solution is
till date, no one has
no,
found.
no one.
Yeah, variational method and all such. Now, there are not many methods one can, of which variational method is I'm very fond of, because you have to make educated guess about the wave function, and you go other way around. You have made a guess of it, wave function, put it back in the equation, get the energy eigenvalue, all sorts of things. And so, anyway, तो इसका कोई एग्जैक्ट सोल्यूशन नहीं।
Okay, sir. Okay, sir.
हाँ
So,
हाँ
sir, I'm scheduling another hour for you where you can continue with this and your numerical solution too.
right
Yes, sir. Yes,
And
sir.
right,
there is a
thank
Thank you so
you,
much.
document for student. The attendance come feedback link is posted in the chat box of YouTube as well as Zoom. Kindly fill it.
right. So
Thank you.
thank you ma'am, thank
No,
you
sir, please
Dr.
don't thank
Poonam,
me,
I'm
sir.
leaving, I'm
Please don't.
leaving, right?
Yes, sir.
Okay,
Thank
Thank
you so
you.
much,
okay,
sir. Thank
Thank
you
you
so
so
much, sir.
much, sir.
We
It's our
appreciate
pleasure
it.
to
right,
host
thank
you.
you, right.
So, students,
So,
we are again making the announcement. We should call it feedback link. Please fill the feedback link, which is given there on your chat box every day. I'm announcing again. Please fill the feedback link and don't write so many mails saying that I missed that link because I left early and so on. Okay, if tomorrow we'll have two different subjects, then we will have two links. These are feedback links where you are supposed to tell how comfortable you are with the classes and so on. And apart from that, those who have joined us for this last 2 weeks only or last week only, when that particular subject is over, then you are kindly requested to send a feedback on email. So when you finish thermal, we will ask you, please send feedback for thermal classes. Solid state is almost over. So you can, at the end of the next week, you can send feedback for solid state physics. Or you can even send now because we already had so many classes of solid state. Right. And what else? Atomic physics. We have had 1.5, we have almost 6 7 hours of atomic physics. So you can write feedback on that, or you can write it together in one mail by doing 1 2 3. That also you can do. for thermal physics or atomic physics, or if you want to not write subject specific, you can write it globally for all subjects or for all classes. And your suggestions are welcome. We are trying to help you as much as we can, providing you with PPT, providing you with material, providing you with numericals, and so on. And Dr. Partha Goswami is very generous. He offered that whatever numericals I have with me, I will share them all. So I said, yes, please share them all. Students can slowly keep on practicing even after the classes are over. So this way, we have kept you connected so that we are able to help you in every possible way. Not every student is connected to so many teachers. Not every student has connection to so many resources. And we have tried to gather the best of the teachers that are in contact with me. Not that these are the only ones, there are several more. And I'm sure that if in the future we do any other series, we will keep you notified if you remain in contact with us. and last but not the least, uh, please attend the classes nicely, not because they're free, but because you are getting knowledge from different teachers. So you hear the same subject from different teachers. Someone will be able to strike resonance with the frequency of your brain. Your brain has an understanding frequency. When it will match with the teacher, you will understand much more, and not just only with the teacher who's able to teach you easily, but also with the teacher who appears not to explain very well, but one fine day you find, oh, this is exactly what he or she wanted to say, and you're able to relate it years later, months later, if you remember. So how you remember, it depends upon your concentration. And I must congratulate you for all those who sit for 3.5 hours. You have to have persistence. Only then a subject like physics enters your brain. So I hope you had a nice time. Even though this was quantum mechanics was not scheduled, I still reintroduced this subject with two speakers today. Two speakers today, and once again last week also you had 1.5 2 hours, because this is one part. If you gain expertise in quantum mechanics numericals, you're able to solve electronics, solid state, statistical mechanics, nuclear physics, and atomic physics all in one go, because everything starts with Schrodinger wave equation. If you understand how to deal with it, how to deal with the potential, how to solve a Schrodinger wave equation, you are able to deal with 5 subjects together. Therefore, the weightage or the time that you should spend on quantum mechanics understanding should be much more than any other subject, because it will lead you to 5 subjects understanding, right? Without understanding quantum mechanics, you cannot understand atomic, molecular, nuclear, particle, statistical, and solid state. Deep solid state requires quantum mechanics. Deep electronics requires quantum mechanics. So you see, 6 subjects, the door is quantum mechanics. And that is why I tried to bring in different teachers so that somebody somewhere will strike resonance with the understanding of your brain. So with these words, we stop today. Thank you all very much. Keep in touch, keep in contact, and do not leave groups, or do not be separated from our connection. Only then we can serve you, help you. If you choose to disconnect in any way, then obviously we cannot reach out. So with these words, Dr. Poonam, please stop the live recording on YouTube. Let the responses be available for another 5-7 minutes for the form, and then please stop the local recording and end the meeting. Thank you so much.
Okay, ma'am.